So here we go. We are learning how to identify and graph arithmetic sequences. All right, and so this matches up with 4.1 in your text. Your essential question today is, what is a sequence and how are sequences and functions related? Okay, so we have learned about functions before. We've learned about linear functions. We can graph those where you have an input and an output. But we're going to look at what is a sequence and then how are they similar to functions? How are they related? And your learning goal today is just, I can identify a rule for an arithmetic sequence that models a situation. All right. So we're going to start with some vocabulary here. These are some new terms that are coming up, such as sequence. All right, and all a sequence is just a list of numbers or objects in a special order. Okay, and you can see there's an example here in this white box. So here's a sequence: 3, 5, 7, 9. Okay, that's an example of a sequence. It's a list of numbers in a special order. An arithmetic sequence is a specific type of sequence, and the difference between one term and the next is a constant. Remember, constants are just numbers. Okay, the same number, a constant. In other words, we just add some value each time, forever, onto an infinity. And so that's what's happening here. You can see 3, 5, 7, 9. The first term is 3. Second term is 5. The terms of a sequence are just the elements or the numbers in the sequence. So that's what these things are here. 3, 5, 7, and 9, those are all terms, and you can refer to them as their order. The first term is 3, the second term is 5. Okay, the comma and then the dot, 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 this means that our sequence goes on forever. It goes on to infinity. And so what is it that we're doing each time here? What are we adding? What is the constant that we are adding each time in this arithmetic sequence? You can type it in the chat, okay? This is an arithmetic sequence because there is the same difference between each of the terms, okay? We are adding some value each time. How much are we adding each time? Anybody want to try it? Just type it in the chat. How much are we adding to 3 to get 5? Thank you, Kobe. Yeah, we're adding 2. 3 plus 2 is 5. 5 plus 2 is 7. 7 plus 2 is 9. Okay, on forever. 11, 13, 15, 17, forever. So this is what a sequence is. This is an arithmetic sequence. It's like a set. Okay, we've looked at sets of numbers. And so it's similar, except the terms in a sequence are in order. Okay, they have to be in order. With a set, if you have a set of numbers, they don't necessarily have to be in a certain order. But in a sequence, they have to be in order. The same value can appear many times. All right, so you may have a number that's repeating in a sequence, whereas in a set, you wouldn't have it repeated because it's a set. So once you represent it one time, you're good. So that would be a set. This is an example. So this is a bracket and a bracket, and we have 0, 1, 0, 1, 0, 1. This is a sequence of alternating zeros and ones. But if I wanted to represent this sequence as a set, well, the set would be just 0 and 1. I wouldn't repeat any values in a set. In a sequence, you repeat everything that repeats because this is alternating back and forth, dot, 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 for infinity, forever. The notation that we use with sequences is the same as the notation that we use with sets. Okay, and we saw this back here. So this example, this sequence had the brackets at the end, and the set version of it had the brackets at the end. So sequences use the same notation. We list each element separated by a comma and then put curly brackets. And these are on your keyboard, all right? I know where they are on my keyboard. They're probably in the same place on a Chromebook. Like if you look to the right of the letter P, are they there on the Chromebook? Because that's where they are on my keyboard. It's like a double use button. So you have like a curly bracket, and then you have just a regular bracket. We put that around the whole thing. Okay, so we can call these curly brackets set brackets, or we can even call them braces. All right, so let's do a slide here. And so at this point, you can, I have this first example done for you. So first one is done for you. We're going to complete the table and state the domain and range for the sequence. And so for number one, we have the value of n, and then we have f of n. So this looks very similar to a function, like a function table, where you have x and f of x, or x and y. But here we have n and f of n. So the value of n, 1, 2, 3, 4, 5, this is actually the domain. Okay, so my domain are the numbers 1, 2, 3, 4, 5. And then f of n, so whatever I'm doing to n is producing this. I'm getting 3, 6, 9, 12, and 15. And so it's similar. Okay, so it's like a function because the same thing's happening over and over again. I have the same thing happening to get to each number. So I go from 3 to 6 to 9 to 12 to 15. This is an arithmetic sequence where we're adding the same amount each time. We're adding 3, right? 3 plus 3 is 6, 6 plus 3 is 9, 9 plus 3 is 12, 12 plus 3 is 15. And so the range, you could think of it, which is similar to like with a function, is 3, 6, 9, 12, 15. All right, so what I'm going to have you do is on your Pear Deck tab, you'll toggle over there, and you're going to do 2. So this is one of your drawing slides. You can just draw in the numbers, or you can use the typing tool to type it in. N is one of your rows here, and you have f of n. And so n, we're going in the same order as we have up above. Okay, so we're using these same values. 1, 2, 3, 4, and 5. So what's missing? What goes in these boxes? What would you put in this box? What would you put in that box? Go ahead and write it in. And then figure out the pattern. What is happening to n? How do we go from this number to this number to this number to this number to this number? We have to, this is a sequence. These are arithmetic sequences. So we got to think, what could we add each time? And what can I put here so it makes sense? So there's 4 missing numbers. You have to fill in those first, and then you list out the domain values and the range values. So everything that's in the top row is your domain. Everything in the f of n in the bottom row is your range. So here's where you need to participate to get your attendance credit. If you don't try, you don't get the attendance credit. Doesn't mean you have to get it correct. I don't care if you get it correct. I mean, I want you to get it correct, but that's not how you get your participation. You need to try it. So go to that Pear Deck tab and write on this slide. So I have 15 of you that have written something. I need 6 more of you to write something. Even just starting it, if you're not sure how to do the whole thing, is there any part of it you do understand? Do the part you understand. I'm up to 17 out of 21 responses. You gotta write some stuff here. So let's let's see what we're writing. All right, so I'm gonna show some of your work. And, you know, if you're not really sure what you're supposed to be doing, come back to the Google Meet tab and see what I'm sharing. Okay, so you can change your answers if you need to. So this person here, they put in a 3 and a 5, and that's correct. Okay, so the first row, our n, it's going up in increments of 1, same thing as up here. And then our f of n, well, I have to think, what can I add each time so that I can fill these in and this all makes sense? Yes, 20 and 40. Okay, so that way I'm adding 10 each time. The domain is all of the numbers up here. 1, 2, 3, 4, 5. And the range is 10, 20, 30, 40, 50. This one's perfect. Okay, that's absolutely correct. That's what you want to have. And so here's another person that did it correctly. So what you can do is you can change yours if you need to. Fill it in so it's correct. They're going up by 10. So this person added a little extra information, which I like. They deleted theirs. This person got it. Okay, that's good. We filled it in here. It's good. Okay, so we did really well on this one. Okay, so a sequence is a lot like a function. And so what I'm going to do real quick is just come back to your EQ. It says, what is a sequence and how are sequences and functions related? Okay, so we just looked at sequences, 2 sequences, and we were kind of comparing them the same way we can with functions. What is the domain? What is the range? That's similar. Okay, we don't have, they are functions in a sense because they don't have any repeating x values. You know, if I wanted to take the domain and the range and actually turn these into ordered pairs, I could do that. We are going to do that. That's our next slide. All right, so here's slide 6. If you want to come to the Google Meet tab so you can see kind of like where I'm pointing to things as I'm explaining this. That's probably good. So the directions say graph the sequence that represents the situation on a coordinate plane. And so here's our situation. Rebecca had $100 in her savings account in the first week. She adds $45 each week for 5 weeks. The savings account balance can be shown by a sequence. So this is another similarity between functions. This, you know, we can represent this as a function, or we can even represent it as a sequence. They're similar like that. And so our y-axis here, we have our savings, all right? And so we start down here at the origin 0, and then each little tick mark, this is 50, and then we go to 100, 150, 200, 250, $300. That's savings. And then along the bottom, we always put time as our x-axis. If you have a choice, okay, to put your time somewhere, if it's some measurement of time, minutes, weeks, months, years, time should go on the x-axis because that's independent. Okay, you can't control time. Time just moves forward. And so here, the number of weeks, we start at 0, 1 week, 2 week, 3 week, 4 week, 5 week, 6 weeks. So if in the first week, she has $100 and we're adding $45 each week for 5 weeks, this is actually going to take on a linear pattern. And so it's going to look like this. So the first week, week 1, $100. And then the second week, we add 45. And then the third week, we add 45. And then the fourth week, we add 45. So we're going up the same amount each week. It's increasing by $45 each week. This is a linear function. Okay, it takes on the pattern of a straight line. It's increasing. And so what you're going to do is you have an interactive slide now. We're going to look at another one. So you are going to now graph the sequence that represents this situation on this coordinate plane. And so our coordinate plane now is a little different. Along the bottom, we still have weeks, right? Starting at 0, 1, 2, 3, 4, 5, 6 weeks. And then the y-axis is donations. So these aren't savings. We're giving money away. This is donations. This person is giving out money. Adam has $300 to donate. That's nice of Adam. And for the next 5 weeks, he donates $60 each week to a different charity. Wow, Adam's really nice. Look, lucky charities. Adam's a good person. His remaining donation money can be shown by a sequence. Oh, so the remaining donation money. So be careful here. It's not asking you to show how much he's donating. It's asking you to show how much is remaining. So when we start at 0 weeks, we have $300 initially. Okay, so the amount of money that is remaining, we're starting here. Your very first point is right here. Okay, and I'll do this one with you. I just need to open it in another tab. Okay, so your very first point, whatever color you want to use. This is a pencil. This is the sizer. Okay, so your very first point, we're at $300 right there. All right, because it's asking you to show is, oh gosh, that's so large. So you can change the size of your pencil because, yeah, sometimes it's really big and it just takes over the entire picture. So we are grabbing his remaining donation money. All right, so we start with 300 for the next 5 weeks. Each week, it's giving away $60. So after 1 week, where's the next point going to be? How much money will he have left after 1 week? Anybody want to chat? Put it in the chat. What should I do with 360? Should I add them or subtract them? I'm going to subtract, right? Thank you, Kobe. Yeah, so 240, you know, 250 is here. So 240 is probably right here. If you change the size of your dots, then it's kind of like crazy. Right? A little bit. I'm trying to make it consistent, and it's not working very well for me. Okay, there you go. All right, and then we're going to move on to the next week. What's happening now? How much money does he have left after 2 weeks? So this is what you guys are doing. You're working on this slide. You should be in your Pear Deck tab, plotting multiple points. Until he's out of money. And so I have 9 of you that have started this. Thank you to the 9 of you that have started this. Everyone needs to participate. And you know, if the extent of your participation is repeating what I have done so far, that's a start. Okay, get that done. I have 12 out of 22 responses. Oh, that one's fine. So I'm going to keep doing this as you're doing it as well. So if you are a little bit stuck. Kobe had typed in here $180, which on the second week, yes, we go down another 60. So from 240, we're down to 180. So approximately that is going to be about right there. And then the third week, okay, 180 minus 60. We're at 120, right? The fourth week. How much money is left in the fourth week? $60. $60 is left in the 4th week. And then after that, week 5, he's giving 60 each week. When does he run out of money? On what week will he donated all of his $300? Yeah, week 5. Okay, so if you come back to just the Google Meet tab, okay, I'm showing you guys we started at 300 and every week we went down 60 bucks. Okay, this is a sequence, an arithmetic sequence, but it's also a linear function. And so by the time we got down here at week 5, he donated his last $60. On week 6, he doesn't have any more money to give. You know, if you wanted to put a point on his donation money, you know, you could, I guess you could technically put it at 0. But I'm not going to do that. I'm just going to leave it like that for right now. And so let's see what you guys came up with. Okay, so someone connected the dots here with a linear, with a line and put the arrows. That's nice. This won't keep going down past the x-axis, and it won't go past the y-axis either. Okay, so we're limited, and we're kind of limited to the first quadrant. So yeah, you could do the, I think the line would be okay. But in this case, there actually wouldn't be arrows. I know I always tell you guys put arrows on your lines, but that's when they go on forever. So in this case, he didn't ever start with more than $300, and he's not going to donate more than that 300. Okay. All right. So slide 9. Okay. When we are talking about arithmetic sequences, there's actually a couple different types of rules. So one type of rule is an explicit rule. Okay, and that's what I have kind of a yellow box around here. For a sequence, an explicit rule for a sequence defines the nth term. So remember, the terms in a sequence, you know, the first term is the very first one, the second term, the third term, the fourth term, the fifth term. And then the nth term is a way of referring to any of the terms, like just a general way of referring to any of them. So the nth term as a function of n for any whole number n greater than 0. And explicit rules can be used to find any specific term in a sequence without finding any of the previous terms. So these are not dependent on the one before it. I wouldn't have to know what f of 3 is to figure out what f of 4 is. I could just figure out f of 4 because the rule here in this example is n squared plus 2. So whatever n is, if n is, I want the fourth term, then what I would do is replace the n with a 4. 4 squared plus 2. 4 squared is 4 times 4. That's 16. Plus 2 is 18, and that's what you can see over here, 18. Right? So you can figure out in an explicit rule like this one, you don't need to know what the other values of n are. You don't need to know any of the ones before it to figure out any certain one of them. You can find out any of them at any time. And so this is as a table showing that. This table now, instead of going across horizontally, we have columns, vertical columns. So we have the n values starting with 1, 2, 3, 4. And we saw that before on those other examples where it was going n 1, 2, 3, 4, 5. Here we're using n 1, 2, 3, 4. This is the f of n rule. So we didn't really see a rule before. They just had the final answer here. But what the function is, or the sequence, is f of n equals n squared plus 2. So whatever your n value is, you square it, and then you add 2 to it. 1 squared plus 2 is 3. 2 squared plus 2 is 6. 3 squared plus 2 is 11. 4 squared plus 2 is 18. Okay. Remember, when you square a number, don't forget, it doesn't mean multiply that number by 2. It means multiply that number by itself. The other type of rule that you can have in a sequence is a recursive rule. So there's explicit and recursive. And in a recursive rule for a sequence, it finds the nth term by relating it to one or more previous terms. So in this case, you can't just figure out any particular value of n you want. You know, you can't just go in and figure out the 8th value. It's because it's dependent on the one before it. So this is an example. If I want to find f of 1, and it's telling me here it's defined as 4. Okay, so the function, when I give the value of 1 to it, I get 4. And then f of any number, n, number n, it's going to be equal to f of n minus 1 plus 10. So these are recursive rules. This rule means that after the first term of the sequence, every term f of n is the sum of the previous term and 10. So f of 1 equals 4. If I want to find f of 2, well, then it would be f of n minus 1. So f of 2 minus 1, f of 1 is 4. 4 plus 10 would be 14. So this is a type of rule that depends on other values of the sequence or the function of n. Whereas explicit, you can figure out any of them at any time. But this depends on the one before it, maybe.